Hello, everyone. It's a great pleasure to be here today. I'm representing our group to share our recent work titled A Reinforcement Learning-Based Intelligent Communication Scheduling Framework for Enhancing Coordination in Distributed Systems. This presentation outlines how reinforcement learning can be utilized to tackle inefficiencies in distributed communications and introduces a framework that adapts to dynamic environments while improving system coordination. To guide you through the talk, here is the structure of my presentation. We will begin with the research background, highlighting the core problem and motivation. Then I will explain the methodology, followed by a summary of the experimental results. After that, we will look at the future improvements to our current approach, and finally conclude with a research summary, pointing out both innovations and limitations. And now, let's move on to the research background. Traditional distributed system often relies on fixed scheduling rules, which do not adapt well to changing environments. They struggle with issues like node failures, network fluctuations, communication latency, and load imbalance. In particular, gossip protocols, though popular, become inefficient under these dynamic conditions. Furthermore, heterogeneous resource demands only increase the complexity, making it clear that more intelligent and adaptive solutions are needed. While some researchers have attempted to enhance communication with methods like static priority rules or dynamic programming, this approach falls short. Static scheduling lacks responsiveness, and dynamic programming is often too computationally expensive. Deep reinforcement learning offers potential, but training costs are high and models are hard to deploy in particular systems. Therefore, there is a gap for a lightweight, real-time adaptive method that balances efficiency and practicality. Our research addressed four primary goals. First, we aim to improve communication efficiency using reinforcement learning. Second, we analyze the limitations of traditional scheduling methods under dynamic conditions. Third, we propose a new framework that leverages reinforcement learning for adaptive communication scheduling. Lastly, we evaluate this framework across different scenarios, including diverse topologies and failure rates, to assess its convergency speed, cost, and fault tolerance. And here is our methodology. The technical roadmap of our solution involves three core steps. First, we model the system states to capture dynamic network conditions. Then we use a Q-learning strategy to guide node selection. During training, we use greedy explorations, while testing employs deterministic policies. Finally, the reward function is designed to reflect communication efficiency, latency, and robustness. This loop of observation, decision, and feedback forms the basis of our adaptive reinforcement learning scheduler. Compared to the traditional ways, we enhance the gossip protocol by integrating it with our reinforcement learning scheduler. While gossip spreads messages randomly across nodes, our method dynamically selects nodes based on learned strategies that account for current conditions. This hybrid approach improves the adaptability of the protocol, making it more resilient to faults and more efficient in communication, particularly in resource-constrained distributed systems. Here are the results for our experiments. Our experiments simulate message propagation in a dynamic distributed system using a single machine environment. We test various node sizes 5, 10, 15, and 20 to check scalability. Key evaluation metrics include communication cost, number of message exchange, and convergency error. The simulation also introduced node failures and network variability to better represent real-world scenarios. From the right figure, the cost ratio between traditional Gaussian protocol and the reinforcement learning-based methods is always greater than 1, which means the reinforcement learning scheduler achieves lower message volume and communication costs at different node numbers. Our, our experimental results show significant improvements. Communication cost was reduced by over 60%, and convergence error dropped by nearly 72%. These gains were consistent across different network sizes and failure rates. The results indicate that our reinforcement learning enhanced approach not only scales well but also adapts to failures more effectively than traditional methods. The success of framework system from three key innovations. First, Q-learning dynamically adapts node selection to current conditions, reducing communication costs. Second, our enhanced Gaussian protocol combined with topology-aware adjustments ensures better fault tolerance and stability. Lastly, the integration of reinforcement learning in scheduling introduced a new methodology that addresses limitation of existing approach in dynamic distributed systems. After that, we will look into the future improvements. Despite our progress, challenges remain. Q-learning has limitations in large and partially observable environments. It's also sensitive to sparse rewards and lacks mechanism for global feedback or higher-level exploration. These factors can affect convergence speed and decision-making accuracy in more complex and large-scale deployments. To address these challenges, we plan to incorporate more advanced reinforcement learning methods like DQN and PPO. These can better handle high-dimensional states and provide stable policy updates. Additionally, we aim to design dynamic reward functions that include early error detection and robustness incentives. We also plan to refine our state space by including more detailed system features like failure patterns and communication frequency to improve decision granularity. Lastly, I will make a short summary to our findings. In conclusion, our proposed reinforcement learning-based scheduling framework significantly improves communication efficiency and coordination in distributed systems. It performs well under various dynamic conditions and scales effectively, while we identify some limitations, particularly with Q-learning's capacity and the granularity of state modeling. We believe our research offers a new, practical direction for intelligent communication in distributed environments. Our work presents an innovative integration of Q-learning with the Gaussian protocol, yielding notable improvements in resource use and fault tolerance. It achieves multi-dimensional performance breakthroughs and provides a new approach for distributed systems. However, limitations such as limited convergence accuracy and coarse-grained state modeling still require further refinement to unlock the full potential for our framework. And here is our reference for our findings. And thank you very much for your attention through our presentation. I welcome any questions or suggestions you might have regarding our work. I look forward to meaningful discussions on how we can further improve intelligent scheduling in distributed systems.